Hi guys, so I'm Rémi Forax and I will talk about JDart. JDart is a port of Dart on the JVM, and the basic idea is Google provide a client VM and I will provide the server VM. Well, I will reuse the hotspot for G9 as a server VM. So just in one slide, Dart is a dynamic language. I mean, the basic idea is to have a better JavaScript. You have currently two runtimes provided by Google. One is a Dart VM, which is basically a V8 VM transformed for Dart. And you have Dart2JS, which is a Java code and now a Dart code that take Dart and transform it to JavaScript to run in browsers that are not Chrome. Basically, something which is really weird from the language perspective is that because you have this transformation, Dart is sometimes less dynamic than Java. You don't have class loading things because you want to do tree shaking to basically Dart.js takes the whole library and only picks the part of the library that are needed for running the code. So the language is dynamic, but you can do a fairly amount of static analysis on it. If you compare to JavaScript, you have real scope. You have classes, you have no such method things really like Smalltalk. You have mirror because it's a Gilad-Bracca language. And you have optional types. So basically for Dart, type are more documentation than something else. You have two running mode. You have the check mode that will check at each call that the type are okay or not, and you have the production mode where the VM run and don't check any type. And for fun, integers are nullable and infinite. You can put null on an int, which really sucks if you want to implement it on Java. Basically because you have a mismatch between primitive ints and Dart ints. So just the Dart VM, it's derived from V8. It's not a production V8. It's a great toy currently. It's a client VM. It's 30 bits only. In 42 bits, it generates 32 bits code. And it's a two-tier compiler. You have a first, at the first run, that code is compiled to assembly code directly. There is no bytecode, no intermediary form. And after a while, if the method is hot, the code is compiled a second time with more aggressive and optimistic optimization. It uses tag pointers, and basically all objects are 32 bits value or small integers in 31 bits or reference. And if you try to just take a Dart code and transform it to Java and using boxing, you have really awful performance. You can't use boxing for that. So basically, my talk is it's on Dart, but you can reuse exactly the same kind of technique that I use for any language that have the same problem, which are how to deal with overflow from basically 32 bits ins to begins and how to deal with ints that can be null. So just I want to show an example on the wrong way to write Fibonacci. In my opinion, there is more code with that way than the other, at least in talk. And I want to see you the generated code, the code generated by Dart and the code generated by JDart. So, assembly code now. I have put the slides on the wiki, so you can just download it, and if you are not able to read the code, it's a little small. So how it works, it's really interesting because it's really like invoke dynamic. I mean, it's exactly the same principle. This is the first code generated, so it's a code which is generated fast and which is not really optimized. So for Fibonacci, the first thing that you have to do is a minus. You say n minus 1. So here you have a call to a runtime stub, and you call it with minus, and you have a special C code in the VM that will do the minus by checking the two argument and knowing if it's a minus between ints or a minus between double and this kind of thing, because it's a dynamic language. And then you call Fibonacci on the result. The thing which is interesting is here you try to do a minus 1, but you do a minus 2. It's just because of the representation of int. The first int are in 31 bits and not 32 bits. You have exactly the same code just after for the minus 2 and the call to Fibonacci. And here you have the plus between the two Fibonacci call. And at the end you have an interesting check, which basically do an incrementation and comparison and a jump. Someone can guess what's this code? What is the purpose of this code? No, it's not overflow. Overflow is done by the runtime routing. It's the hotspot detection, hot code detection. The hot code detection is done at the end of the code and not at the beginning. We will see that it's interesting. And this is the code generated if the code is hot. If the code is hot, the code is generating again, but in that case you have the code is generated in an optimistic way, which is the runtime now knows that we only use integers, so we will do a check if the bit say it's an integer or not, and if it's not an integer, we will do a deoptimization. So we jump to go to a deoptimization. So in that case, we can use sub to do the subtraction, so n minus 1, and call the Fibonacci function, and exactly the same thing for n minus 2. And here we have the plus. Here the plus you have the plus which is here, and you have a jump on overflow if it can overflow, and in that case it will do a deoptimization too. So basically the idea is we know that the code run enough and without anything different from ints. So the code is specialized for ints. So basically, the idea is to do exactly the same thing in JDart, but because it's hard. I think it was 2 years ago, I have presented PHP Reboot, which has exactly the same.
We're having a audio problem. I think we need to replace the battery in your wireless mic.
Which one?
This one.
The one.
Yeah, that's not really supposed to fiddle with all that stuff. Hopefully this will work. Actually, which way around was it? I think it's the other way, wasn't it? Well, it's definitely a stronger battery. Say hello.
Hello? Oh, hello? Oh, better. Okay, so here is one of the trick. 2 years ago, I have done exactly the same thing with PHP Reboot, which is to first have an interpreter that profiles the code and then generate a bytecode with the profiling information. The main issue with this kind of code is how to implement the de-optimization. Because we are in Java, you have to implement the de-optimization in Java, and it's not that easy to implement it. So I have decided to use another way to do the thing, which is try to generate a bytecode that will be read by the VM in a way that the VM will generate exactly the same kind of code as this one. It's a little bit like matrix. If you know how it will be generated, how the JIT works, you can try to generate a bytecode in a way to have the assembly code that you want generated by the JIT. Let's do that. So JDart, it's basically Dart on server because we will use a hotspot, and hotspot is really slow the first time you run it. And the idea is to remove boxing, or to try to not have boxing. How I do that, I first do a kind of precise static type analysis. It's really ugly from the research perspective, but the idea is to have a static analysis which is linear but precise. We will see. And I use the split, what I call the split path trick, which is the way to tell the VM how to generate the code I want. So the main issue is how to deal with overflows. And I think you can reuse, if you have a language that have overflow, exactly the same techniques. So what kind of static analysis is done? It's an interprocedural static analysis, but the main issue, because it's interprocedural, it can take a lot of time. So it's really like inlining. The basic idea is you will not do a real interprocedural analysis, but just enough interprocedural analysis, really like when you have an inlining horizon, you will do something which is enough to generate good code, and so basically I have timers that say if I have enough time or not to do more analysis or not. It's mostly linear. We will see why. And by default, the analysis don't trust the type written by the user and do a flow analysis. It's much better. And the main purpose of this analysis is try to separate integers, double or primitive types from object. I mean, all objects will be will use invoke dynamic. There is no problem. There is no boxing with object. The main issue is to try to avoid boxing with double or ints. And the result of the static analysis is kept, or part of the result is kept to drive the generation of the code, which is done later. And there is some trick to try to share the analysis because you have an horizon in your algorithm. You can have two call sites that will share some part of the analysis, basically. So just on Fibonacci, I will just use this example to show you how it works. We will do with my hands, and if you want to read a paper, you have to wait until December. I have not finished to write it. So it's really a precise analysis. It starts with the main called Fibonacci with 7. So the analysis knows that this is 7. It's really precise. It's not an int here. It's 7. So because it's 7, I know that this code is never executed for that part. And I know that here Fibonacci is called with 6. So I have no analysis of Fibonacci with 6. I need to do another analysis, but I will do this analysis not on 6. Otherwise, I will do the analysis for all calls of Fibonacci, which is not a great idea. In that case, I will promote the int to a positive int. And so you have a promotion, and the promotion is bound. So the analysis is kept linear because of this. And it's promoted to positive integers that are promoted to in 32 bits integer and to big ints if it's not possible. So with positive int, this code can be called. I know that the result is 1 in that case. Because it's a flow type analysis, I know that here n is 2 or more. Otherwise, I will be in that case. So I know that n minus 1 can't overflow here, and the same here. The main issue is now I call Fibonacci here. The first call of Fibonacci has to use the return value, but the return value is not calculated because it's a recursive function. In that case, this is the only case I trust the type given by the user. Only in checked mode. In production mode, it will be object. And I will do the boxing. So an int in Dart is an infinite int that can be null. Here, because I do a plus on int, I know that now this is not null, because if it's null, I will generate an exception. I do a plus something. So basically, the result of Fibonacci is something which is an infinite int but not null, because it's the result of plus. And so on. So here I know the result type of this thing, so I know the result type here. And as I said, I try to only keep. Here I see that now I have two versions of Fibonacci, one with 7 and another with a positive int. And there is no difference in the result type. So this version is not needed. This one is enough. So basically this kind of inference will allow me to avoid to do here and here the overflow checking, because I know that n-1 and n-2 never overflow. The only overflow that I can have is just here on the plus. Now the generation. So the static analysis give me information. I know if I know basically if it's an object, if it's an int which fit in a 32 bits int, or if it's a kind of big int. The idea is now to say that usually users don't want big ints. Why? Because they are really slow. They are not. The operations are not constant. Usually, if you take a look to the bugs reports by users, like by example in Python, you have bugs reported because users see a performance cliff at some point, because the runtime just transforms an int to a big int. And in that case, you have an order of magnitude of performance loss. So the idea is, when you generate the code, I will generate the two paths. The path if it's an int and the path if it's an integer. And I will hope that the VM is enough smart to remove the code that use the integer, because this code is never called. So here is in pseudo Java the code generated for Fibonacci. I generate the bytecode directly, but it's less readable. Basically, the idea is to say, I will generate two Fibonacci. I will say by default, Fibonacci will never overflow. If it's overflow, I will generate a new version. So my Fibonacci always return an int. It's not fully true. It can return a big int, but in that case, I will box it in an exception and throw it. Okay, it's a special case. Anyway, the VM will do a deopt. No problem. And for each value that can be a big int, I will use two slots, one storing the int and another storing the big int. And the idea is just to use the null check to know if the big int is used or if the int is used. And because the VM don't generate this kind of call, I mean, the JIT, perhaps you don't know that, but the JIT doesn't do the null check. If the check is always true, you have a kind of implicit check, which is done. And so the idea is, if I generate a code like this, what's the hotspot VM? It's exactly the same with G9. What the VM will generate is just a code that will do the invoke dynamic. And because the exception is never generated in the optimistic in my optimistic version, the VM knows that underscore R1 is null. So the VM knows that only this part of the code is called, and this part of the code is never called. So the VM will generate a deopt at that point, because there is no need to generate this assembly code. So here is the code which is generated by hotspot. So as you can see, -1 is dec, -2 is add with -1 on the register that was decremented before. You have the call to Fibonacci here. Here you have the jump on overflow. There is no jump on overflow in the current VM, so I have this code, which is a hacker delight trick for weirdly here I should have the fast pass here, but in fact the fast pass is here, and I have a jump here, and here I have the deoptimization which is done. It's not that weird. In fact, it's due to the fact that when hotspot will generate the code, the call to Fibonacci will not be finished. So the VM will not have enough profile information, so don't know how to reorganize the if. It's not a big deal, but it's funny. I think it's why Google do the hotspot, the hot code check at the end. Because if you do it at the end, you know that the code was run at least one, so you have a profile. Yeah.
So Rémi, on your previous slide, you have the split. That's what you call the split path.
Yes.
Where you use an exception to return a second value occasionally.
Yes. Never.
Never.
That's basically the idea.
So are you relying on the JIT to keep those paths separate always via deopt?
Yes.
Because the form of your code merges the paths back in aggressively.
Yes, but because you merge with a null check, it's okay.
Okay. So I'm trying to imagine whether this trick would be formulated differently if you had a way to return two values.
It will be better, clearly better.
Exception to propagate the second
Yes.
value. 2 balls!
So just a benchmark on Fibonacci with 40. This is the result of the Dart VM currently. This is the result if you write the code with boxing in Java. And here you have the result with Java with int only. You have the result with JDart. Yeah, JDart is better. I don't know why. No, it's not invoked in them. If you take a look to the generated code, it's similar. I really don't know why. It's perhaps a kind of alignment or something like that. I don't know, but technically it's a little bit faster. And here you have the code, and JDart, if you deactivate the fact that the JIT inline recursive calls once, which is more like the code generated by Dart VM.